today we continue discussion about dynamics. So as I explained, we have, no, to my taste, it is more or less satisfactory formulation of dynamics in case of motion within a convex set. By the way, this formulation is good for even non-regular convex sets with non-regular boundary. No, say a segment of a line is also not, its boundary is not everywhere regular, its endpoints are just sharp needles. So, today I wanted to consider the following situation. We have, say, a surface, S, and consider the motion of a material point which is forced to stay on this surface without friction. The surface S is inside, say, Rn. First, how does it look for a smooth surface? S is smooth. So at every point of this surface, we have a tangent plane, which it is point x. We have tangent plane T at the point x, and we have the normal plane N at the point x. Yeah? And the motion equation is x of t trajectory at every t is on x. X dot of t is tangent to the surface. And most interesting, the acceleration x double dot of t is orthogonal to the surface at the point where this particle is. This last statement is called the D'Alembert principle. So the D'Alembert principle is that the acceleration of the point moving freely without friction along some surface is orthogonal to the surface. No, surface, I mean better to say a manifold, because dimension of S can be arbitrary from 1 to dimension of the space. No, if the dimension is equal to n, then we have in fact no constraint, and nx is just a point, so it is 0, and this means that acceleration is 0, and we have the constant speed. Next interesting case is when the dimension is 1. When dimension is 1, so it is a motion along some curve gamma. No, this is essentially the case which I'm going to consider today. So all these this system of three equations describes what is maybe called motion along the geodesic. So solution, we can write this in the form of differential equations, which I don't need, so I don't write it. And this equation of geodesics on manifold S, which is embedded into the Euclidean space. The problem, this becomes, I would say, problematic when the manifold S is not smooth. Namely, this gives a good equation for geodesic if manifold S is twice differentiable. So that the tangent plane has, I would say, good derivatives along S. Then the geodesics make sense. If the manifold is less regular, then it becomes unclear what will happen. And so we have to start thinking from the beginning. Now I wanted to make some step aside and say that the manifold which is really interesting here is the manifold of positions of fluid filling some volume. Instead of Rn, we have the space of all positions of all fluid particles with no constraints, so each particle moves independently on others. Yeah? So it is some huge Euclidean space, infinite dimensional. And the positions which are interesting are when these particles are confined into some domain and fill it with constant density. This is some manifold some set in this infinite dimensional space, and this set it is not much known about the structure of this set, but one thing which I wanted to tell you is the following. If you have this set, say D, I draw it like a curve, in fact it's infinite dimensional, then we can introduce the following characteristic of its regularity. We take 2 points, x and y, and we consider the distance between them. And in fact, what is the distance? We have here 2 candidates for the distance. One distance is just distance along the straight segment between them. So it's real distance in the ambient space. Other distance is we consider all the trajectories, all the curves connecting x and y, and which are going inside this D. Take a length of each of these curves and consider infimum if this infimum is finite. Yes? So we have the D of xy. It is the length, the infimum of this length of the curves which go along this set D and connect these 2 points. And we have simply just L2 distance between them, because the space which is ambient for this D is just L2. And what can be said about relations between these 2 distances? Now, clear that D of xy, this is the distance if you go along our set, is cannot be smaller than the distance if you go straight from x to y. Yeah? But can we say something more positive? Is it at least finite? And it turns out that we have the following estimate. So distance between any two, I would say, positions of fluid is less than some constant times this distance along the straight segment to some power alpha. Yeah? No, in case of three-dimensional fluid, what I can say is that alpha is approximately equal to 7. Yeah? Some strange exponent. So we have this set such that distance along this set can be estimated through this distance along the straight segment like this. This, yes, how to compare with a smooth manifold. If D were a smooth manifold, then of course this alpha should be 1. Yeah? So we see that this manifold is very far from smooth. Yes, and so it is far from a situation where we can apply this D'Alembert principle in this regional form. Yeah? No, we can consider the more elementary, apparently elementary situation, as I say, when our manifold is just a curve gamma, so we always move to the curve. So what can we assume? Assume that the tangent line to this gamma, say in a curve in the plane, it is already C non-trivial. The tangent line to the gamma C x gamma everywhere exists and depends continuously on the position on x. Yeah. So this means gamma is C1, a little more than 1 plus alpha. Yes. So this curve, say direction of this curve, depends continuously on x, say Hölder continuous. Yes? In this case, we can say that this second equation also makes sense. And what about the third equation? Yes? So let us start this work. So for a smooth curve, we can perform the following construction. Let us take initial point x0 and initial velocity. No velocity, say v0. Yes? And now let us give some time step, say tau. And let us do the following. Let us perform the following construction. This curve is by no means a convex set. So my construction looks like superficial like was in previous lecture, but in fact it is quite different. Consider y0 equals x0 plus tau times v0, y1, x1 that means projection on gamma of y1. Projection means the nearest point. We can also take, say, this is, say, y1, consider direction which is orthogonal to the velocity, and take this x1. So something which gives a point on the curve which is nearly closest to the point y1. This is x1. But now what is the velocity at this point? And we write v1 is projection on the point, on the tangent space to the point x0 of v0. So what does it mean? It means that we approximated our curve, we had a curve, we approximated it with this piecewise linear curve, yes? And this curve has discontinuous direction of tangent line, yes? Every time when we reach the point where this line, approximate polygonal line, changes direction, the new velocity is projection of the old velocity on the new direction. That's it. So we have a new pair x1, v1, and then we continue. Y n plus 1 equals yn xn plus tau times vn, xn plus 1 equals projection on gamma of y n plus 1, and v n plus 1 is projection on t at the point xn, vn. Yeah.
So the v1 should, I think, be projection of a v0 on the tangent of x1, no?
The tangent of x1, yeah. Of course, thank you. Yeah. So these are the chain of equations, and this behaves much better than the previous chain. Why? If our set where we are forced to move is not convex, and then there is no control over velocity. Velocity, if you consider our solution is just the chain of points, sequence of points, and the distance between successive points can grow. And for non-smooth situation, not smooth curve, it can grow really fast. So therefore we cannot use this simpler method which I described last time, cannot use in general situation. Here, because of this,
the last line,
excuse me?
last line, is it a tangent of xn plus 1?
N plus 1. Yeah. Thank you. v n plus 1 is always less or equal than norm vn. Now, this method, it is even can be used in, say, computational problems when you have some tricky surface and we are constructing a geodesic. We can use this method and it works. And the theorem, I think it is can be found in the books of differential geometry. If not, it can be proved without difficulty, is that when, so if S is twice differentiable surface, then x1, x0, x1, and so on goes to some limit gamma of t, when tau goes to 0, where gamma of t is unique geodesics on S, gamma of 0 equals x0, gamma dot of 0 equals v0. Yeah. So this approximate solution converges to true geodesic. So this prescription, so what I described here can be regarded as a prescription. We are in a situation when we don't have real definition of trajectory. What is trajectory is not defined. So in courses of mechanics, trajectory is defined as solution of these differential equations, after all. Or something equivalent, say some variational principle. But we cannot explain it. Both differential equation and variational principle, they, if you open all the brackets, they also are describe some finite construction which goes to where we have some parameters, this tau, which goes to infinity. So the I would say status of that definition and the status of this definition these statuses are the same. So we give some prescription and say that this prescription, what it defines, is our trajectory of mechanical system. Yeah. Well, simply because mechanics is not mathematics and it requires its own axiom. So axiom can have the form of such prescription. So we have this prescription, and I can write it in more say rounded form. X of t is on S, x dot of t in t x of t s, and we write v of t equals x dot of t equals, let me first write it, product as projection of the point T x of S of V of 0. So here I write this symbol. It is called, I call this ordered product of projection. So we take all S between 0 and T and take projection, so let me write it. Let me write P of S. P of S for any S, P of S, family of projections in, say, Rn continuously, family of projections, let's say 1D projection, continue depending on S. Yeah, so we have, so what is 1D projection? 1D projection is a projection of a vector on a line. Yes, so this line rotates continuously when S changes. So it is family of projectors. And now let us write the following. Let us write S0 is 0, less than S1, less than Sn equals T, for example. And we write P of Sn times P of Sn minus 1 times P of S0. Yeah, so no, as usual, it is product of operators, so we first do this, then this, then this, and so on. Let us take this and equals P S0 Sn this projector, and we consider the limit P S0 Sn limit as maximal, say, model sk plus 1 minus sk goes to 0. Yeah? So instead of taking just all the points between 0 and t, we take discrete points. No, as everything which we did such a discrete approximation. And this is product P of S of T. Yes, so this product is defined by as this limit. So we take many points S0, S1, and so on, and consider the product of these projectors And then we take the limit if this limit exists, of course. Yeah. Now let me have a first look at this definition. What is this? So we have a vector, say it is V0, yes, and then we project it on the line at the point S1. So what is the length of this projection? No, this is angle alpha, yes, and so this is V0 module V0 times cosine alpha is approximately equal module V0 times 1 minus alpha square or 2, if alpha small. Yeah? Now consider this curve. The curve is gamma in the plane. At every point we have the direction of the unit tangent vector. It forms with horizontal line the angle, say, alpha of S. What is S? S is a natural parameter along the gamma, the length parameter. Yeah? Alpha of S. And then we have P of Sn, P Sn minus 1, P of S1 V0. What is this? We first perform this projection. No, length of V0 times 1 minus alpha 1 minus alpha 0 square. Alpha 1 is this angle at the point x1. This x2. It is here. It is alpha 2, and so on. 1 minus alpha 2 minus alpha 1 squared divided by 2, and so on. 1 minus alpha n minus alpha n minus 1 squared divided by 2. And this is I assume that alpha is continuous function, so each of these terms is small, so it is approximately equal V0 times e to the power minus sum alpha k plus 1 minus alpha plus 1 minus alpha k square divided by 2. K from 0 to n minus 1. Yeah? 2 relates to this. So here we have this sum of squares of increment of a function. So if our function alpha of s, let me write alpha k equals alpha of xk. Yeah. If our function is differentiable, with continuous derivative, then this is sum goes to 0 as the number of points increases, the distances decrease. Yes? Because it is what's called quadratic variation. Even if you have here the first degree, then you have a finite limit, the total variation of the function. And with square, of course, it goes to 0. Here enters this quantity, quadratic variation. Alpha equals, say, upper limit when n goes to infinity and maximum model xk plus 1 minus xk goes to 0. This quantity alpha k plus 1 minus alpha k square. Let me write alpha xk plus 1 minus alpha of xk, all this square, k from 0 to n minus 1. Yes, so this is quadratic variation. It is well-known subject in the processes. So, quadratic variation, and we have approximately the following estimation that V of S is equal V of 0 E minus square, say, V of T. E of alpha. Yeah. Divided by 2. Yeah, so it is quadratic variation. So the question, where is here non-standard analysis? Yes, where it is. We have, in general, we have trouble with this formula because it can happen that one and the same function, alpha of S, can look different under different magnification. So we can imagine a function such that it looks, in our scale, looks quite hairy, yes? And then if you looked under some magnification, we'll see that no, it is a smooth function. And if you look at much larger magnification, we see no, it is also again hairy, but in a much smaller scale, and so on. So if you will estimate this quadratic variation of the function, then it can happen that there is no convergence. We can easily construct examples of functions such that when n goes to infinity, this quantity does not converge to anything. Yeah? And so it endangers all our construction. And so we have to use some machinery of non-standard analysis, which we already have. Now, say we first of all this construction of successive projections works together with construction of the chain of points. Yes, so we keep to that construction. So we write, we take tau, and we construct the following chain of points and vectors. Y k plus 1 equals x k plus tau times v k, x k plus 1 is projection on gamma of y k plus 1, and v k plus 1 equals projection on t at the point x k plus 1 of vector v k. Yeah. So if you, yes, and initial conditions, we have x0 and v0. This is initial conditions. And we construct this chain of points, this chain of vectors, and then we say these points are all on the curves, x0, x1, xk, and so on. They are on the curve gamma, and we can somehow interpolate it so that we have a continuous curve. Say we move along gamma with constant speed between every 2 points. Okay, and so we have a solution x tau of t. Tau is parameter. And for any tau, we have positive tau, we have some approximation to something, some approximate solution. And now let us embed our universe into non-standard universe. Yes? Go to start view. Then you have star of this function x tau of t. Now here tau and t belong to star R, and x tau of t belongs to star gamma. So again, this object, what we get here, of course, depends on the non-standard model, as usual. so it is non-unique. No, let it be. So it is non-unique, everything depends on the model. We saw that, say, solution of differential equation with continuous right-hand side also depends on the model. So after we performed this embedding, we take the standard part of what we get here. One moment. Next is, let us take tau 0 in star r plus, and tau 0 infinitesimal. So instead of going to some limit, we take it already infinitesimal. Yes? And then we perform the following trick. We take standard part of what was here, x to 0 of t. So tau 0 is fixed. So it is a function of non-standard t. Yeah? So how to take the standard part of non-standard function? We have to take all the pairs t x of t, yes, r, all such pairs, and then consider the pair standard of t, standard of x of t. So this is the materialization of our general notion of standard part. And if you take the set of all this, where t x of t x of to 0 of t, yeah? If you take the set of these standard parts, yes, it is automatically some standard set, because it's set of pairs of standard numbers. Yeah. So what we get is this is x of t. This is our trajectory. So again, for different models, for different infinitesimal steps to 0, we have different solutions. And this is, I would say, necessary evil, because solution is really non-unique. It can be non-unique. So why it should be unique? Yes, we have I would say transcendentally complicated system, so there is no obligation to be unique. Okay, but there exists one case when we have a unique, no, more or less unique solution. And let me tell you about this case. the function alpha of S. S is a length parameter, x of S, is a typical realization of linear process. So, should I remind what is linear process? Okay, linear process is a random function w of x and omega, such that omega is a random parameter, yeah? Such that x2 minus x1 is independent of w x1 minus w x0. Yes. Let me say w y2 minus w y1 if x1, x2, intersection y1, y2 is empty. So if you have two non-overlapping segments, then the difference of values in in the ends of one segment is independent of the difference on the other segment, and distribution of w x2 minus w of x1 is Gaussian with dispersion phi times model x2 minus x1. So it is a process with independent increments, and the distribution of this increment depends only on the distance between 2 points. So it is the linear process. Now the typical graph of the linear process, I think you saw it, is also called Brownian motion, looks like this, very hairy. But fortunately it is not the curve gamma itself, its first derivative is the direction of the tangent to the curve. And there is a theorem, the basic theorem of the linear processes, that for any I would say probability of the following event. X1 less than x less than x2. W of x equals modulo x2 minus x1 equals 1 for any x1, x2. Here. So here we have a very strong, I would say, uniform second variation is growing linearly. And so let us consider the case when alpha of s is this W of s omega, typical. Typical means which satisfies this condition. So its probability is 1. Yeah. Now, by the way, it is interesting to look how does such a curve look. To have a picture. No, it is easily constructed by computer, so I did it today, so here it is. You can see it. You can take it. Yes, it is one of infinitely many examples. So you see nothing unusual. It is some strange spineless curve without any character. Yeah. It is differentiable at every point, so no problem. And if you consider this curve, take this curve, then you have the following thing. Consider the v of s. It is speed at the point s. S is the distance 0. S is the distance along the curve. So it's a natural parameter or natural coordinate along the curve. And from this and the previous, you can say that v of s equals v0 e minus s over 2. Yeah. So this curve is so I would say hiddenly rough that it really breaks the motion. So we have the following differential equation: ds dt equals, let's take v0 equals 1, e minus s over 2. So the point is moving along this curve, but with deceleration. 0. So we can solve this equation. No, I taught differential equation several times, so I did it thoroughly. Let me write the answer.
It's a linear form.
Excuse me?
It's a linear form.
Excuse me?
Linear form. So this is like a differential equation. Is a linear form.
It is not
So-
linear, it is autonomous.
Or, sorry, autonomous. Yes, sorry.
Yes. S of t. No, okay. E to the power s over 2 ds equals dt. Yeah?
Yes.
This means 2 e s over 2 equals
T plus C.
t plus t0. T0 equals 2. Because if t equals 0, then this equal, just a minute, this equals 2, yes, and should be e to the 2 equals 0 plus t0, so t0 equals 2. So e to the power s over 2 equals t power plus 1. No, okay. T equals 2 e s over 2. Just a minute. No. S equals 2 logarithm t over 2 plus 1. Oh. Okay. And ds dt equals, so we have to differentiate this, 2 divided by logarithm 2
It's a 2 by t plus 2.
huh?
2 over t plus 2.
T plus 2. Yes. So we see that the speed decreases to 0 when t goes to infinity. Yes, but nonetheless we can go as grows to infinity. So this is a really strange phenomenon because there is no friction here. Yeah? So this strange result is obtained without friction. So it is completely because of non-smoothness of this curve. So is it possible? In fact, it is really strange. And here I have to say a few words how did I come to these problems and why I regard this seriously. There is a fundamental phenomenon which is called turbulence. turbulence. And in turbulence, we have experiments, I think millions of experiments, which show very similar behavior of the fluid. Yes? So what is the sort of experiment? No, original experiment of Reynolds. So we have a pipe, and here we have the motion of the fluid, say water, with some rate, flow rate Q. It has some length, it has some diameter. The fluid has some viscosity. It is every fluid is a little bit viscous. That's all. And because here is some viscosity, we have to apply some pressure drop. Here is P0, here is P1. P0 minus P1 equals delta P. So we applied this pressure drop to simply sustain the fluid flow. And delta P depends on all what is written here, on Q, mu, L, and D. Yeah? Now, if you keep Q, L, and D constant, and very just mu, so you, I think, can take different sorts of liquid, or take a liquid and change the temperature somehow. Yes? Then you have the following dependence, which is the most famous graph in mechanics. How does delta P, this pressure drop, depends on viscosity. So for high viscosity, we have a linear dependence. Yeah? So the pressure drop depends linearly proportional to viscosity, strictly proportional to viscosity. Then something happens, which is called turbulent transition, and then this dependence changes, and we have this behavior. So delta P goes to some limit, delta P0, and delta P0 is definitely positive. This means that however the viscosity is small, the pressure drop, or the rate of energy dissipation, of energy loss, remains nearly constant. Yeah? Now, this experiment is made in the pipe. It's also possible to measure such things without pipe, without walls, say in the open ocean. Yes, so there is an ocean turbulence, and people are measuring and see the considerable rate of energy dissipation, while the viscosity is really negligible in such large scale. So this is the experiment, possibly the best, the most reliable experiment in the whole physics. And so we see that there is no explicit friction, no explicit viscosity practically, and we have considerable loss of energy. What does it mean? How can we explain it? This is the main riddle of turbulence. So turbulence is a mysterious thing because of this. Otherwise, it would not be so principally interesting. This, of course, it's called dissipative anomaly by physicists. Physicists love to give good names and sometimes they think that it is explanation, but it explains nothing, just the term. So what happens here? Yeah? One approach is that the fluid flow becomes turbulent. This means that its velocity field is very fast changing in space and in time. So this is because of this there is some energy loss, and even people derived some formula which shows the rate of this energy loss because of this irregularity of the fluid flow. But why this irregularity? Yes, and here we can go down to what I said about the fluid. So the fluid, in fact, is moving not in our, I would say, not only in our physical space, but in infinite dimensional space of its configuration. Yes, and it moves there along some set, which is the set of its admissible configuration, admissible position. And that set is quite irregular. I showed you approximate degree of its irregularity. No, in some directions it is more regular, in some direction is less regular, but this means that we have to consider the motion along this irregular set. The details of this irregularity are still not known. Yes, and in this case, we have seen it in a simple example of motion along a curve. But just imagine that this curve is not a curve, but some infinite dimensional set, and we are moving not in the plane, but in the infinite dimensional Hilbert space. Yes, and you can appreciate, so it is not so easy, but the principle is that if you assume that the motion along the non-regular surface or non-regular set is such that the energy dissipates, yes, and the mechanism is due to our definition of solution. By the way, there is no good definition of solution for the fluid. We don't know what is really definition of turbulent flow. We have it every day, but we don't know what it is. We have no mathematical definition. Yes, so this is one of possible definitions, and at least it gives us a clue to what happens so that we have this dissipative anomaly. So this is the reason why I pursue this topic, because it may be maybe it brings us closer to the mystery of turbulence. Okay, let's finish today and continue next time. I almost finished making problems, so you will have them soon.